Hello, hi everyone. Welcome to the Temporal Graph Reading Group this week. This week we are glad to host Zifeng, who is presenting their recent work, zrLLM, uh, zero-shot relational learning on temporal knowledge graph with large language models, which was accepted at um, NAACL for 2024. And for more information on our speaker today, um, Zifeng Ding is now a computer science PhD student in the group of database system and data mining at the Ludwig Maximilian University of Munich, or the LMU Munich, uh, supervised by Prof. Volker Trest. He is a nominated PhD of European Laboratory for Learning and Intelligent Systems, and co-supervised by Prof. Michael Brownstein at University of Oxford. He is also a researcher at the Siemens AG Group. And I will hand the mic to you.
Okay, hello everyone. Today let me give you a short introduction about our recent work, zero-shot relational learning on temporal knowledge graphs with large language models. So yeah. Okay, first let me give you a short introduction about our work. So as stated in the title, we are dealing with a data structure called temporal knowledge graph. I think some of you might be really familiar with that already, but I'm still going through some basic ideas. So temporal knowledge graphs are multi-relational graphs for storing the factual information. They are derived from the static knowledge graphs by incorporating the time information. And we can use the fact quadruples to represent the temporal knowledge graph facts in the form of zrOT. So they represent the subject entity, relation, object entity, and timestamp. Since the word knowledge is ever-changing, it is very important to indicate the time validities of the facts to improve the expressiveness of the knowledge graphs. For example, in 2020, the Chancellor of Germany was Angela Merkel, but in 2022, the Chancellor of Germany became Olaf Scholz. So as we have seen that the word knowledge is ever evolving, which means that the temporal knowledge graphs are also ever evolving. So there has been a lot of interest in forecasting the facts that will happen in the future, and a lot of models are proposed to solve this problem. So for the traditional models, if you pay attention to the left side, the traditional TKG forecasting method do it in this way. For example, we want to forecast some fact happening given some timestamp. We first will take this timestamp and then search for the historical graph information. And based on this graph information, we will learn the entity and relation representations. And then we will predict the unobserved future facts based on these representations. Since the graph is ever evolving, so as time flows, we will observe a lot of new facts, and we want to forecast them. And we also will see a lot of new relation types, which did not exist in any previously observed fact. So this kind of problem will cause another consequent problems in the traditional methods, because traditional methods, they require a large number of training examples regarding each relation to learn the representations, as shown in the left pipeline. And they will fail to inductively model the new but unseen zero-shot relations. What we have done in our work is that we actually are the first to draw attention to study these kind of zero-shot unseen relations in the context of the forecasting in temporal knowledge graphs. And we design a large language model-based model to enhance the recently proposed embedding-based temporal knowledge graph forecasting methods in reasoning these unseen relations. And our model can help to substantially improve these models' abilities in forecasting the facts containing zero-shot relations, and they can also maintain their ability in forecasting the facts with seen relations. After I give you an introduction, you might know that, okay, we are dealing with some new problems, so we have to define our new task. And since it is a new task, we also need to propose some new coupled benchmarks. So our new task is called the zero-shot TKG forecasting. Assume that we have a ground truth graph, GGT, and we also have a set of relation denoted with R. And this set of relation can be split into two parts. First part is a set of seen relations, and second part is a set of unseen relations. And we make sure that the unseen relations and seen relations are disjoint from each other. So to do the link prediction, we were given a link prediction query where the relation of the query belongs to an unseen relation. And we will also have some observed facts, which are stored in the ground truth graph that contain the seen relations and happen before the query timestamp TQ. So the aim of this task is to predict the missing entity in each link prediction query. It can either be the subject entity or the object entity. And for the new benchmark data sets, since we're dealing with some new tasks, we have to have new benchmark data sets. But we also need to pay attention to the information leak problem of LLMs. So most LLMs become viral after 2020, and they have seen the word knowledge up to 2020. But in the most popular TKG forecasting benchmark dataset, they are constructed based on effects before 2018. For example, ICWS 14, 05, 15, or 18. So this will incur information leak if we use LLMs to do TKG forecasting on traditional data sets. And we actually have seen several models, they are published and they actually have the information leak problem, but they still, maybe they will fine-tune, maybe they are fine-tune the language models or use in-context learning of large language models to forecast the facts that happened before 2020. So we think that this might incur some problem and we want to fix it. So how we construct new benchmarks for these new zero-shot tasks? Actually, we adopt the pipeline just similar to the few-shot link prediction problem in the static knowledge graph. First, we will find the knowledge base that contain the facts happening after 2021, and we will collect all the facts within the time period from the associated knowledge base and then sort them in a chronological order. And we will split the facts into two splits, training and evaluation. And evaluation facts should happen after training facts to fix the forecasting setting. And we will compute the frequencies of all relations in the evaluation split only and set a frequency threshold and take each relation whose frequency is lower than the threshold, which means that they are already few-shot as a zero-shot relation, and treat every fact containing it in the evaluation split as the test data. And we will exclude the facts associated with these test relations from the training split to make sure that during training model have never seen them. And the rest of the facts in the evaluation split are taken as the validation data. And we have to emphasize that we actually design our models to perform well on both the facts with seen relations and unseen relations. So maybe we develop a model that help us to enhance the zero-shot ability for these traditional models at the cost of sacrificing a lot of performance on the seen relations. This is undesirable. And here is
just a quick question. So when you are removing the zero-shot relations, do you also remove the node? So the nodes, you have all seen them. It's just the relation that's being removed. Is that correct?
Relation. Yeah. There are no inductive setting in the entities. So actually, we made sure that all the entities in the test data are seen during training. Yeah.
I see.
Yeah.
Okay. Thank you.
And this is the dataset statistics of our datasets, and we can see that all the facts come from year 2021 to 2023. And then after we have a new definition, new benchmark, we can see how we develop our model to do that. So here is the model overview. We also want to notice that our model is coupled with the embedding-based TKG focusing methods to enhance the zero-shot ability. If some of you have a very great knowledge of temporal knowledge graph reasoning, you will know that we can actually classify the models into two classes. First are the embedding-based models, and second are the rule-based models. I would say that the limitation of our work is that we cannot couple our method with the rule-based model because we need to include the representation from the natural language space to the graph space. But there's a plus of our model is that I would describe it as a plugin or adapter because it can be coupled with ideally any embedding-based TKG forecasting model because yeah, it's very adaptable. So how we do it? First, we use the GPT 3.5 to generate an enriched relation description for each relation. And we will have the relation text provided by the TKG datasets, but these relation texts are very short and concise. That's why we want to enrich it. And we will input the enriched descriptions into the encoder of another LLM, T511B, and align its output to the TKG embedding space. And we will employ another relation history learner to capture the temporal relation patterns based on the natural language relation representations. And some of you might be curious that why there's a difference between the training pipeline and evaluation pipeline. I will dig into some deeper details in the later parts. So first, let's see. Yeah, please.
Sorry, I have a quick question on the enriched relation descriptions. Can you give a bit of an example of how the enriched relation descriptions look like?
It's on the next slide. Yeah.
Thank you. Sorry for interrupting.
No problem. Yeah. So how we do that? First, let's just start with these examples that are shown in the table here. So on the left column, we see that this is the provided relation text in the original data set. On the right column, we see that this is the enriched relation description. Before we did the experiment, we assumed that okay, that the right column should contain more semantic meaning or semantic information compared with the left part because it gives a more detailed explanation of how of what this relation should represent. This is motivation of why we want to do that. And how we do that, how we achieve that, we use the GPT 3.5. We just input as a batch of these relation text from the left column using the prompt stated here, denoted with this yellow plus purple blocks. And then we want the GPT 3.5 to give us more comprehensive details of the relation text. And we think the text on the left is not enough to include enough semantic information, or at least we say that we can improve that. So, but there will also be some information leak problem if we use ChatGPT or GPT 3.5. It is because GPT 3.5 was released in 2022, which means that if we are trying to forecast the facts in 2021, it will have some problem. So how we try to avoid this problem, as shown in the prompt, we did not show our task of TKG forecasting, which means that GPT 3.5 doesn't even know what we are doing. It just follows our instructions to give the explanation. And after we get the output, we will also manually check the descriptions generated by it and make sure it generates relation explanations solely from the semantic perspective, but without any word knowledge. Like if you pay a closer attention to the table down there, you will see that there is no word knowledge contained in any enriched description, just to avoid any information leak from the word knowledge. And after we have this, we have some enriched description. We can use the T511B's encoder to encode each relation and get a encoded representation of each relation. And we will map each word representation to the dimension of the forecasting models to achieve the alignment from natural language space to the graph space. And we will use another GRU to model the sequence. The sequence is actually the encoded embedding of the enriched description. And we will take it as the relation representation. And the last part is that we will substitute the original relation embeddings, which are trained from the graph context, just directly to this text embeddings in any TKG forecasting model. But we have to pay attention that the LLM-based models are fixed to preserve the semantics extracted from LLMs. Let's take an example. For example, we have a lot of graph context about one very frequent relation. If we don't fix that, during the backpropagation in the training, the embedding of this relation will be largely changed and will be largely decided by the graph context. And we cannot build any bridge through the natural language embedding from seen to unseen relations. But if we fix the embeddings, the relations with closed meetings will naturally have highly correlated text representations, and it will build a connection on top of the natural language space, but not the graph representation space. So
there is
yeah.
a comment from the audience.
Yeah.
So we could ask, so we could ask the model also to evaluate if the description is somehow temporal dependent. I guess this means to ask the large language model.
I mean, let me check the text. We could ask
you can
the
check the
model also to
evaluate. Or feel free to like unmute yourself if you want to ask.
Yeah, I'm not sure what is the meaning of this. Like, I mean, are you saying we can do that, or let's say we can also add this step to further prevent information leak? I'm not sure, but from my perspective, I think yeah, but it's not fully controllable. As I play around large language model, I think if some of the word knowledge is too fine-grained, not like trained on Wikidata or Wikipedia or something. For example, these event-based methods, the large language model cannot very easily distinguish the timestamps very easily, because ICWS, this kind of data set, they have the time interval between each timestamp as 1 day. And 1 day is not very coarse like in Wikidata, which is 1 year. Like Wikidata is much easier to for us to consider this temporal dependency, but for 1 day, it's like highly moving and very dynamic graphical flow. I don't think large language model can help us very easily to, or very accurately to decide whether there is some information leak problem or not, whether it has it or not. Sometimes it cannot answer this question. Sometimes it will say, okay, I have never seen it, but it doesn't mean that it has never seen it. Maybe it's because that the stuff we are asking, the query we are inputting into the large language model is not able to extract it, the information we want from them. So yeah, well, this is my comment. Yeah.
Yeah.
Okay.
So thanks for the comment. Yeah.
Yeah. I'm not sure, like, if you have follow-up questions, you feel free to just to shoot it. Yeah. Okay. So then after we have this stuff, okay, we have a new relational representation, and we can have but we also want to increase the text to graph alignment. We think it's not enough. Why we think it's not enough? It's because inspired by the traditional temporal knowledge graph reasoning methods, they actually take the historical graphical flow and try to model this flow, and then try to predict whether this flow will affect the future. So we also want to capture this kind of stuff with the help of our natural language based representations. So we developed a model called Relation History Learner, and it is actually just capturing the historical relations stored in the observed graph and try to give us some hint about the future. For example, here we have 2 facts. The first fact is that on 2022, January the 4th, China grants diplomatic recognition to Nicaragua, and after 1 week, China signed a formal agreement with it. So here there stores some pattern, is that first, the subject entity will grant the diplomatic recognition, and then it will sign an agreement with the object entity. So the intuition of introducing this relation history learner is just to use the text-based representation to capture this kind of flows in a temporal knowledge graph. So how do we do it? Given a training fact, now we see we have zrLT, and we search for the historical facts containing both entities before the timestamp. And we'll group these facts according to their timestamps. So for example, we have a fact at T. Now we will have a sequence of T groups containing the facts happening at each timestamp before T. So for each group, we will pick out the relations of all its facts and form a relation set. So in each relation set, it will be all the relations happening between S and O at a specific timestamp before T. And we will compute the entity relationship of between 2 entities in this entity pair at each timestamp with an aggregator. It's just like weighted sum of the relation representations at each timestamp and use another GRU to capture this recurrent flow. After we have this, we say, okay, we can do it in training, because in training we have seen all 4 elements in every fact. But during test, record the definition of our link prediction task, we will see that, okay, we have some missing entity. It's either the missing subject entity or either or the missing object entity. So we need to solve it with another prediction framework. So we solve it by introducing another simple history prediction network, and it is just an MLP. It will output a historical pattern, a predicted historical pattern denoted as h-hist tilde. And we will impose another training loss of this prediction network with an MSE. So this MSE means that, okay, the predicted history should be as close as the ground truth history during the training. And during evaluation, we just directly use the prediction network to output this h-hist tilde because we don't have h-hist, ground truth h-hist anymore. So we want it to predict the correct relation history. For example, given 2 entities, A and B sign formal agreement now, we want this prediction network to realize that these 2 entities have already had an improving relationship with each other. After we have this, we just directly take this output from the prediction network and input in one step of a recurrent state to get the final relation patterns. And we use another KG score function to measure how much 2 entities match this relation pattern. This score function is inspired by a static knowledge graph embedding method, Tucker. We just directly copy it, and we take this score as the RHL-based score. After we have the RHL-based score, we want to incorporate it into the original model. So we have a total score function of the model. We denote it as phi total, and it can be decomposed into 2 parts. First part is the phi prime, which is the original score function of the original model, and we will add another weighted sum with the RHL-based score. Since RHL-based score is solely based on the text representation, it will help model to consider the semantic information when we reason the zero-shot relations. And for the final stage, for the loss function, if you pay attention to the bottom part of this slide, you will see that our loss function can also be decomposed into 2 parts. So the first part is a loss of the original model. We call it model-based loss. And the right part is all the loss function regarding the relation history learner. So we add them together to form the total loss. So
there was a raised hand in the chat. Do you want to ask the question?
Yeah, let's do it. Yeah, please.
Yes, I have a question. Could you please go back to the part with the historical components? Here, my question is, here you will do something with the entity pair and with its historical information. Here, suppose we have a situation for one entity pair, and for this entity pair, we need to predict it with an unseen relation. However, between these 2 entity pairs, between the entity pairs, there are no historical relation given in the past.
Yeah. It will be denoted with a dummy relation.
Okay.
Yes, if there is no given, because actually this is a very interesting question. For example, we have 100 timestamp before the considered timestamp, right? We cannot make sure that for this pair of entities, they will have relation at every timestamp. So every time it exists, we will substitute it with the dummy relation. And the dummy relation, its embedding, it will be shared with all entity pairs when there are no historical relationship between them.
Okay, thank you.
Yeah. All right. Then if we go back to the model pipeline, we will see that why there are some difference between the training and the evaluation pipeline. And here I denote every block with respect to the relation history learner with the blue blocks. So other blocks will be exactly the same. It's just a difference between the training and the evaluation by using the history prediction method. Okay, then let's see how we do the experiments. For the experiments, we have considered some very recently proposed method or very classic and popular methods. So we consider the SciGNet, Tango, Tucker, Dismode, RGCN, TI-RGN, RETI, and CNet. And we couple our model with these methods and try to perform our new task on our newly proposed benchmarks. And for the evaluation metrics, we use mean reciprocal rank and hits at 1, 3, 10. They are widely used in all kinds of temporal network forecasting papers. And we want to re-emphasize that again, that the zero-shot performance is evaluated when models achieve the best performance on the validation set, because we want them to perform well on both kinds of relations. Here is the table. There are too many numbers in it. Actually, the conclusion is that our model can greatly help the TKGF models in forecasting effects with the zero-shot relations, which is what we want them to do. And in most cases, surprisingly, we found that it can even improve the models in predicting effects with scene relations, which was unexpected. And we have also done an ablation study to demonstrate the effectiveness of the enriched descriptions and the relation history learners. We found that they are actually very important, and they can help us to consistently improve the model performance. And we have also switched the T511B to T53B. We want to study that the size of whether the size of the LMs can decide the performance of the models. And we have seen that T53B leads to the degrading results. It means that the larger size of LMs will be more effective. Another experiment is that we have tried to compare our zrLLM enhanced model with the recently proposed language model-based TKG models. We have chosen two models. First is a PBT and second is ICL. So PBT is fine-tuning on a bird to do the TKG forecasting with the masked language modeling. And ICL, they don't tune any large language model. They use the in-context learning with a very huge size GPT new X20B, but they don't change the parameter of the model. So we have also seen that tuning representations based on larger LLMs are more effective. Maybe it's not shown in this table now because I have not posted the results achieved by our models with them together. But if you're interested, please refer to our paper because there are across two tables, and if you compare the numbers between these two tables, you will know the difference. And also we have concluded that in-context learning without tuning is not strong enough. And also we have seen that for the ICL in-context learning, even without fine-tuning or parameter-efficient tuning on large language models, ICL, it actually takes up forever for you to do the link prediction on a very large scale data set, because doing the inference on large language model are also very time consuming. Lastly, I want to give you a case study for our relation history learner. So we ask our zrLLM enhanced CNET, we call it CNET Plus, and another model like enhanced model, but without relation history learner to predict the missing object of this link prediction query. United States reduce or stop military assistance, blah, 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 2021, July the 3rd. And we observe that our complete model can predict the ground truth answer African Union perfectly, but without RHL, it will fail to predict optimally, and it will give the answer Afghanistan. So to study it, first, we want to plot the nearest ground truth history between United States and the ground truth entity African Union to see how is the historical relation patterns between them. It is shown in this figure A. And we have seen that they actually have a worsening relationship between these two entities during this time. And then we try to change the history on June the 17th from negative to positive. For example, here we see I hope you can see my cursor now. I think you can see my cursor. So criticize or denounce is a positive relation, is a negative relationship. And we change it into defend verbally, which indicates a positive relationship between these two entities. So the relations marked as red is the relations that we changed in figure B. And in figure C, on top of figure B, we even changed the relation happening on June the 24th, also from negative to positive, which means that from A to C, we gradually change the semantic meaning stored in the relational historical patterns between these two entities. And then we use the history prediction network to output the representation of the predicted relation history. And also we encode the relation histories in A to C with a history encoder. So here A, B, C are the same repeated figure from last slide, but here we see that we plot the TSME of the predicted history, encoded ground truth history, and changed history 1 and changed history 2 from the figure A, B, C. And here the dashed line, the number beside the dashed line denotes the distance between two dots. And we have seen that the predicted history is closest to the ground truth history. And the changed 1 version from figure B is closer than changed 2 version from figure C to the ground truth history. The reason why change history 2 is much farther than a ground truth history is that actually it changes more negative relationships to the positive relationships. So it changes more in the semantic meaning. That's why it is becoming farther and farther from the ground truth history. And this can help us to indicate that our history prediction network can capture the semantic information stored in the relation history. And also, we have plotted the nearest ground truth history between United States and Afghanistan. So Afghanistan was the 4th answer returned by the model without the relation history learner. And if we take a closer look at this figure, we will see that the green history between United States and Afghanistan, it indicates a much better relationship than compared with the histories in this pink or red block. So the relation in the query, recall that it is reduce or stop military assistance. It is a worsening, it indicates a worsening relation history because it originally represents a very bad relationship between two entities. So if we can use the RHL to capture these relation histories, our RHL can help us to naturally exclude the candidate entities that do not fit into the relation patterns. For example, here, the Afghanistan, it has a better relation history. So our RHL will realize, okay, this kind of relation history will never lead to a positive relationship between two entities in the future. This is the basic intuition and idea behind relation history learning. Thank you very much. I think I have finished. Yeah.
Okay. Yeah, so thanks for the very interesting presentation. And feel free to ask any questions in the chat or just like unmute yourself from the audience. Can you go back 2 slides? I just have I think this case study is very interesting, but I'm just thinking that what if you are not changing the semantics or the text itself, but you are changing the timeline of events? So you should expect that if models capture temporal dependency correctly, and let's say your ground truth is still A, and then now you change, instead of like June 24th, you change to September or something, then your embedding space should be moving away, right? So you should be further away from the truth. Like when you ask queries, because the thing is, like in practice, when you ask for queries, you don't know when exactly things are going to happen in the future. You can just do a rough guess. So how does that change the embedding space of the models? And then how does the time granularity of the model that perceived will kind of affect how they can like predict the queries in a sense?
This is actually, I'm not sure I have understood your question very well or not, but I'm trying to answer it. So regarding the time granularity, I would say that from the last question, I have said that if there is no relationship between two entities at a specific timestamp, we will use a dummy embedding to replace it, right?
Right.
So it means that the GRU sequence in modeling the relation history will be the same all the time. It doesn't matter. It doesn't matter what kind of relationship between two entities at any time. So I would say that if the time changes, the sequence will be different, right? The position where there are values of the sequence will change. For example, we have 5 previous timestamps. We have 2 entities that only has relationship at the first timestamp, and we change it to the third timestamp. We will see that first there will be dummy information, dummy and prediction. Or before change, it will be information, dummy information. I believe that the model will react to it, but I never did any experiment on it. So yeah, that's my gut feeling of it.
So basically the dummy relationship helps the model to understand how much time gap or how much difference in time delta t has happened between events.
I think so. Yeah.
But as you go to more finer grain time granularity, your dummy relationship is going to be increased like significantly if you go to daily like versus like annually, right?
Exactly. That's I know you're doing temporal. I know you're doing dynamic graph. I have read a lot of paper of you, so I know why you will ask this question, because you deal with a lot of continuous time dynamic graph, right? So if it is continuous time, I would say that it is completely different from how we do in temporal knowledge graph, because temporal knowledge graph are discrete first. Continuous time dynamic graph is different because I would say maybe at a specific, maybe Unix timestamp, there will be only one link happening, or some but it is different. In temporal knowledge graph, most recent methods, they still try to model a static graph snapshot happening in a period of time, maybe one day. The time granularity is very huge. It is different from the continuous time dynamic graph. So how we do it in dynamic graph, we just find the historical historical temporal neighbor of the link we want to predict, maybe U and V. We find the historical one-hop neighbor from the temporal and use maybe transformer to model this sequence. This is how they do it, but it's only pay attention to U and V in one link. But in temporal knowledge graph, people don't do that. People just first learn the static structure at a specific timestamp of all the entities and the relations, and then try to put this embedding into some recurrent structure like LSTM, GRU, or transformer, and then output for all the entities, the embedding at the future timestamp. So it is quite different. I would say it is not very easy to adapt to the continuous time dynamic graph. Yeah.
Yes, so basically we have the discrete time dynamic graph, which is what the setting you are dealing with in temporal knowledge graph.
Yes.
However, I think like depending on your task, like I think it's really about the task. So not necessarily about the model themselves, but depending on what task. Like, so if you're predicting when certain like events will happen, like some war or some sort of some arrest or some kind of like operation, that you might need some fine grain like time granularity, like up until like hour, for example, right?
Yeah.
And then for some other tasks like getting married, you might for the yearly, that's fine, you know. So it depends on the relationship itself, actually, in a sense.
Yeah, and also we have another very popular data that's called GDLT. GDELT dataset, its the time granularity is 15 minutes.
Right.
But unfortunately, the people studying GDELT, they only focus on maybe 1 month in total. Like 1 month in total, even if the time interval is 15 minutes, there won't be too many timestamps. So in most TKG forecasting methods, a lot of them actually just pay attention to the nearest historical timestamps. For example, just 4 timestamps behind or 10 timestamps behind, which is not very easy to capture a long dependent in the temporal axis, long dependency in the temporal axis. This is a problem. Actually, I'm also trying to solve this kind of problem in my new project. So I cannot give a very, it's not about secret or not, because I also don't know how to do it. And it's something that we need to figure out, because like recently a lot of paper, they mentioned the long temporal dependency in the dynamic graph. But I have read a lot of paper. I don't know what exactly means long temporal dependency. Do we really need long temporal dependency? Like, do we really need to model everything before this timestamp? Or do we need to select something important from a very long historical, from a very far away historical timestamp? I still have no clear answer of it.
So that's definitely still like open question. And just like for the audience, there's people congratulating you for the talk as well. And also feel free to go, since we are more in the discussion phase. So I think that's a very interesting question. And we also have some projects that are working on kind of related aspect that should come out soon. But I think that's something that's kind of a very open question, depending on the specific relation, because there are relations that are more just in the short-term memory, but there are also highly recursive relations that do happen on the weekly or something like that. So it depends on how what type of relation you want to model, and also I think the time granularity of the data set and task. These things don't have to be coupled together, right? You might have on a data set some relations that are more fine-grained than the other ones. Like, for example, so talk about the Wikipedia, you have some dates that are very specific, like Christmas is on December 25th of each year. And that's not a yearly granularity. It doesn't make sense to model it as a yearly granularity, while some other specific knowledge is on the yearly only. So I think there's a lot more interesting question to ask, and how to capture these dependencies. But yeah, so not to bring the discussion too long, and thanks so much for the interesting talk.
Yeah. Well, I also have some comments about what you're talking about. Yeah, I mean, there are some people just discussing how to do it, because what you mentioned is that some of the relations actually, or some of the facts, let's say, they happen periodically, right? Some of the facts, they happen more randomly. In temporal knowledge graph, there are some papers trying to do that, but I also agree with you totally, is that it's more ideal to develop some model that is not coupled with the datasets. We should find something that can do somewhere in the between, that it can help us to model the dynamic graphs that is more dynamic in the temporal dynamics, like in the temporal flow. And we can also use it to model something that has very long time granularity, or at least distinguish the fact which has longer periodicity or more randomly. Yeah. Are you doing something like that now?
Yes, so we will have something related to that in the Europe submission, but I won't say too much about it. So, but you will see it in 1 or 2 months. And one of the questions from the audience is, can the slides be shared?
I'm not sure. I think, yeah, if you want, yeah.
Yeah, so if you send us the slides, then I can put it on the website. And I think,
yeah. I don't know, do you think this slide is okay? I'm not sure, because I just did it yesterday. I'm sorry.
The slides are very good. Yeah.
Okay. So it looks, everything is clear. Okay. Yeah. Okay. Nice.
Yeah.
Nice.
Yeah,
That's
it's very clear. That's why there are so many questions.
Okay.
Yeah. Okay. So let's wrap up the talk here, and then so hopefully we can have more discussion if we have chance to meet in person, or over some other opportunities. And so I will wrap up the reading group here. Thanks.